Thank you. So I'll be presenting some work on distance-based fair regression and classification, which is based on two projects, one regression and one classification, and I'll give a brief overview of both of them. And this is a joint work with my two supervisors, Emilio Caizosa and Dolores Romero Morales. So this is an overview of what I'll go through. I'll start off briefly talking about fairness in machine learning. What is it? Why do we even care about it? So fairness is becoming more and more important as a topic, as machine learning and statistics is being used more and more in decision making, both either to fully automate decision making or to assist humans doing some sort of decision making. It's especially important in high stakes decision making, so where decisions have a large impact on someone's life. This might be the case in healthcare, the judicial system, or in finance. So whether or not you get a loan for a house, whether or not you get access to a certain treatment, whatever it might be. And so it's important to ensure that these algorithms don't disproportionately negatively affect certain groups, especially if these groups are based on sensitive characteristics, as we say. So that might be race, gender, religion, many of which are protected by law as well in many countries. And so we refer to this group as the protected group, and then we have vice versa, a non-protected group. And fairness has been considered already in many cases, just to name a few, linear models, tree models, Bayesian models. So there's a lot of work being done right now within fairness, and this presentation will add to it. So these are two examples, real life examples where there was bias detected or unfairness detected, and it was then brought to the attention of the public. So the first one is about risk scores in healthcare. So risk scores were used to assess whether or not someone should get access to a specific treatment. And it was shown that it had racial bias, so it was disproportionately badly calibrated for certain groups. And so they weren't getting access to treatment that they should actually be receiving. The second one is a very famous example in the literature, the COMPASS algorithm. So it was used to judge the risk of recidivism, so the chance of committing a crime again, and based on this, whether or not you would be getting parole. And it was found that Black individuals scored worse on this score, even though they shouldn't, and were then less likely to get parole. So a sort of a subfield within the fairness literature, there's been an increase in the use of statistical distances to achieve fairness. So in this case, the goal is to minimize the distance between predictions of a protected and a non-protected group, or classification, whatever it might be, or some sort of dissimilarity. It doesn't have to be a distance in the proper sense. And there are three ways you can do fairness. You can do it pre-processing, in-processing, or post-processing. And this approach, or these approaches I'll show you today, fall into in-processing. So we add some sort of constraint or penalty in order to ensure fairness in the training process itself. This usually gives us more flexibility. There is an inherent trade-off between error or accuracy and then fairness, because in the beginning, the starting point was finding the most accurate model you could. So there's some trade-off between this, and it's easier to control if you penalize or use a constraint. And these are just some of the distances that's been used. So KL divergence, Wasserstein distance, Hellinger distance, total variation, which is just some of them. But the approaches using these haven't really been doing it in processing, so during training. And that brings me to the first project, which is fair lasso regression. So we're in a regression setting. We have a set of predicted values, and it's on those predicted values that we wish to enforce some kind of fairness. This starting point is a basic lasso model, which is just linear regression with a constraint. In this case, you could also penalize it, a constraint for the size and number of variables used. And so using this model, we add a fairness constraint and build upon it, which means we end up with a trade-off between three things: error, sparsity, and fairness. And this is just an illustration. This is for a law school data set where we're predicting first year GPAs, and these are sort of used to roughly sort through applicants for law schools in certain areas in the US. So this is just a lasso model with no fairness constraints, just a classic model. We have a protected and a non-protected group. The blue dotted line is the 90th percentile. So in a case such as law school admission, you won't usually be looking at the whole distribution of predicted GPAs. You'll have some sort of cutoff, some decision threshold that you're actually making this decision on off of. And so what we try to do in this project is focus the fairness where it matters, so around the decision threshold. So in this case, we look at the tail, so above the 90th percentile, and we say, okay, we want a similar proportion in the two groups in there. Obviously, we'll affect the entire distributions, but that's where we focus. The argument being that you can then have a better trade-off between error and fairness. Yeah, so the goal is to make one distribution more similar to the other, or both of them similar to each other. And we do this through a dissimilarity measure, or a distance. And so the starting point is just adding it as a constraint. We say we only allow a certain amount of dissimilarity between these distributions. Obviously, as I just mentioned, we can apply this just on a subset of the distribution. So in this case, the tails. And it's from this that we sort of build our model. We choose this as our dissimilarity measure, and it's the proportion of individuals from one group minus the proportion of individuals from the other group above the tail. So we have binary variables, delta, indicating whether or not you're above this threshold. And then we, of course, take into consideration different sample sizes, but we want that to be small, or at least less than C, which is some value we choose. We can't just have that alone, so we add supporting constraints that we need in order to make sure we actually have the right threshold and we're doing the right things. So constraint B and C ensure that whether or not an individual is above the threshold. This infinity norm of the features times B is actually a big M constraint. So we just assume that we've normalized to 0 to 1 range, and then we can sort of get a tighter bound on the constraints. E is just our dissimilarity measure, which I showed, and F controls the actual threshold. So pi is the percentile we wish to control, and then that corresponds to an actual number of individuals, so a number of deltas that should be equal to 1. Yes, so we test this on 2 different data sets. A law school data set and income survey. The first one I'll look at is the income data set. So this is the mean squared error on the y-axis, the unfairness, so that would be the left-hand side of our constraint on the x-axis, and then for different values of b, which was the lasso budget parameter. And the takeaway from this is 2 things. One, you'll see the trade-off. So you can see we can either be really fair, but that has the worst error, or we can improve the error, but that will cost us in terms of unfairness. And we maintain, sort of, roughly speaking, the same slope for different values of the b. So we maintain the same trade-off. We're simply shifting around where on the scale we are. But the trade-off is sort of maintained. And this is just zooming in on one of them so you can see it a bit better. So same slope, trade-off between error and unfairness. And you can see it's, from the first one to the last one, it's probably, about double. This illustrates some of the same things, but combines all of it. So these numbers come from running the experiments 10 times on 10 different samples and then averaging them. And so on the x-axis now we have the average number of features used, which there's a connection with the b parameter. as shown before. And again, we see this trade-off existing even for different number of features used. Yes, this is now the exact same thing, but for the law school data set. And you might wonder where all the dots went. Well, since our dissimilarity measure is discrete in the sense that an individual is either in the tail or not, and a lot of them might be infeasible or just not change the value at all. So it will be data dependent and parameter dependent whether or not you can actually change the solution. So in this case, we don't have a lot of options to choose from, but we maintain the same slope across the different values of B. In this case, it might make even more sense to zoom in as there is a trade-off even if they looked quite close before. And here we actually have the opposite pattern than we did before. Still error, average number of features used. But in this case, we can actually be really fair, even if we use a lot of features. And this illustrates, just to connect it to the first plot you saw, and this is out of sample. So after our approach, you can see that the distributions are more similar just in general, but particularly in the tail where we wanted it to be similar. And we have distributions being very close. Okay, so that was the regression project. That brings me to the classification problem. So this is a project called Wasserstein SVM. So we're now in a binary classification setting, and we measure fairness on the predicted classes of individuals. So our approach is based on support vector machines, and there's a picture illustrating what that looks like. So essentially, we're separating the data points as well as we can, and we can make it non-linear and do a bunch of things. But this is just a simple linear case, just to illustrate the point. It has the following dual formulation, which might look familiar to some of you. The important part is to pay attention that this is kernel-based, which we will return to later. And that when we solve this problem, we have a score for each individual. And it's based on this score that we do our classification. So we have some threshold, and then we say, okay, if an individual has a score above 0, then they're classified in the positive class. There is obviously here an inherent assumption that one class is good and one is bad. Otherwise, fairness might not make too much sense. And here we see, before we introduce any fairness at all, what the distribution of scores might look like. And as you can see, if the threshold was 0, then a lot more people from the non-protected group would be in the positive class. And likewise, a lot of people from the protected group would be in the negative class. And you can see the unfairness is sort of maintained even if we move the threshold around. But you can make it better or worse. So the way we measure fairness in this case is through the Wasserstein distance, when we use the empirical distributions of scores, and then we solve this transportation problem. So it's essentially, what does it cost to move one distribution over to the other? A small cost means they're close and that they're similar. And the important thing to note here is that while we solve this, we get a optimal transport map, which is essentially saying this individual moves this much score to this other individual so from the protected to the non-protected group or vice versa. We penalize a large Wasserstein distance in the objective function of the SVM, and that becomes our Wasserstein SVM objective. So that's how we improve fairness. So in this case, it's a penalty as opposed to a constraint before, where we use the empirical distributions and we control the trade-off with the parameter tau. And so we can make the distributions extremely similar, but that will obviously cost us in terms of accuracy. Now, this is a difficult problem to solve since it involves another optimization problem just to figure out the Wasserstein distance, but we can make it easier. We can simplify this which brings it back to the transport map and the kernel. So this is the proposition from the paper. The thing to note is that we can essentially rewrite the kernel using the Wasserstein distance. So the very top, you have the original kernel, and then the Wasserstein term rewritten, expressed only using the original kernel and a fixed transport map. And that turns out that it itself is a kernel, thus it can just be plugged into the original SVM framework. And this lends itself very nicely to an alternating algorithm. Like I said, it's a difficult problem to solve to optimality, but it's very easy to alternate between the two things. So you get the SVM solution, then the Wasserstein solution, and then you can calculate the new kernel, and then you're back at an original well-known SVM problem. And this is a flexible approach with respect to the threshold. Since we're making the distributions more similar, we can place the threshold whenever we want. We don't have to choose it beforehand or afterhand, whatever it might be. And we will still be more fair in general. And if we make them completely similar, then of course the threshold doesn't matter in terms of fairness, just in terms of accuracy. And so it actually satisfies or improves two different fairness measures that are well known. So statistical parity, which is just the probability of being classified in certain classes equal between the two groups. And then the strong demographic is just having this threshold independence. So I think I'll go a bit quickly through it. Yeah. Okay, good. So this is a summary of the results tested on 3 different data sets. You'll notice probably a similar pattern as before. We can improve the Wasserstein distance, so the fairness, quite dramatically, without sacrificing much in terms of accuracy. But then if we really want to enforce complete similar distributions, then it will cost us a lot. So that's not easy to do. So the sweet spot is probably somewhere in the middle. You get, when you visualize it later, you get sort of an elbow rule where there's a kink in the curve, and then you have a dramatic drop off in accuracy. And that's sort of the same across all data sets. But it's a bit easier to visualize it. And that's exactly what we see here. We have sort of a flat beginning of the accuracy curve, but a drastic drop in the Wasserstein distance. But then there's diminishing returns, so the Wasserstein distance curve flattens out, and we start sacrificing a lot more accuracy in order to achieve a more fair classifier. This is what it looks like when we visualize the scores. So as you can see, the right plot is after our fairness approach, and the distributions are a lot more similar. You can also see that it's easier to move the threshold around and then still have a fair classifier. And that's also why it doesn't really matter that we shifted the scores. Their value doesn't really matter if they're similar. They can be wherever. We can just move the threshold in order to classify individuals. Same thing for the COMPASS dataset, although to a less extreme degree. So flat beginning, a nice trade-off, and then if we really want to enforce the distributions to be the same, we sacrifice a lot in terms of accuracy. And this is what it looks like. It has a more fair beginning in the sense that the distributions are more similar than the other data set, but we can still make it even closer together, which sort of looks like it concentrates on a few points of scores. Yes. So to conclude, we've been able to make both regression and classification fair by using techniques from mathematical optimization. We can significantly improve fairness without losing much in terms of accuracy and error. And for Wasserstein SVM, we've shown that using the Wasserstein distance turns out to be sort of natural in the sense that we can construct this fair kernel that fits into the existing framework of SVM. Yes, that's it. Thank you. Thank you.
So I want to ask, are there any questions?
I just to the question, like, what are you using to solve the model, and they are solving in exact, an exact way or the approximation?
So the first one,
Both the last second order like both of them are convex, or
the first or the second?
both of them?
The first one is a quadratic program with linear constraints. But the binary variables obviously make it difficult to solve to optimality for large data sets. So what we do, I forgot to mention that, I believe. What we do is we essentially just take a subsample and use that for the difficult constraints, but maintain in the objective function, we maintain the entire data set. So that wouldn't be solving it to optimality, but we could for small data sets. Yeah. So it's a sampling approach, essentially.
What are the dimension of the data sets? For the regression, or for the first one?
Oh, I think we have 20,000 and 5,000, something like that, observations.
20,000 rows.
Yeah.
Can you go back to the model where the regression? You're using the square, the square residuals, the square residuals, right?
Mm-hmm.
The pattern, the hypothesis you pose the fairness. But the constraint is, but still the objective function is quadratic, and you will solve with the quadratic objective. Can you use a non-quadratic, for example, the absolute value of the residuals, so you can linearize and get rid of the quadratic part of the objective function, for example? Or would that change your approach? The approach change, but this can have sense. But the measure of the error you are taking into account is the mass.
Is it what?
Which error are you considering for the train test or this validation? The graph you were showing?
Yeah.
After that, which is the measure?
Mean squared error.
Mean square error.
Yeah.
Just a silly question. In the last table of the sort that you show the accuracy.
I show what?
And the last, the table of that one.
Yes.
The accuracy is in the total sample, or is just in the non-protected?
Total, I guess.
Yeah, it's in total in the test set. Yeah.
No, because I mean, I would expect that when the Western obtained distance is small, then the accuracy in the non-protected part of the sample would improve. I don't know if I'm explaining well.
It would improve.
Like the prediction for the non-protected individuals should be better now that you are reducing the noise.
Yes, maybe compare like the accuracy without considering
the part of
the protection sample, and then.
Oh, so separate it into the two groups.
And then
Yeah.
that one maybe the result better. I don't know.
Yes, but you are doing.
For the accuracy.
Yeah, it could be. Yeah.
But just using the non-protected part of the
Yeah. No, that's a good point. I don't know what's going on actually. But it could be that it's improving and then maybe we're just sacrificing a little bit of the protected group.
Yeah, because for example, the combat example for black people, maybe now the results are better. But in general, as you have more white people, that's
Oh, yeah, that's a good point. Yeah.
So, additional questions? Okay. There's a question online. What other distances could be chosen? Why did you take the was and the was distances? Sorry.
Yes, you could use other distances. Um, I think in principle you could probably use quite a lot if we're just using an alternating approach. So as long as you can calculate it and then add a penalty to it in the objective function of the SVM. Whether or not they would fit as nicely into the framework with the kernel, I doubt it. I don't think they would. So I think that's the Wasserstein part is fitting into the kernel framework. But sure, you could calculate a distance and penalize it easily.
So there are no more questions. We usually ask speakers. Okay. So we usually ask our speakers about their experience in academia. In this case, I think that you're in the first year. So maybe if you want to tell us about everything, about anything about your experience so far.
Oh, it's been great. I mean, I'm in my first year, but I worked with Dolores for 2 years beforehand.
Oh,
I think it's been great. I've gone to a few conferences and met a lot of great people, so I think that's awesome. Yeah. No, I love it so far.
okay. Great. So please,